Chapter 18 is talking about new family. So for chapter 16, we talked about aromatic compounds, how to name this compound, some physical property based on the solubility, like the intermolecular forces, and the have to name, like the parent name of phenol, toluene, aniline, benzoic acid, benzaldehyde, and then the positions of ortho, meta, para. We also learned about how to determine if the molecule is aromatic, is non-aromatic, or is anti-aromatic. In chapter 17, we covered about reactions for the aromatic compounds, which were, in general, you had electrophilic substitution reaction, which you bring a strong electrophile to replace a hydrogen from benzene ring. Nucleophilic substitution reactions, you have to bring a nucleophile to replace a leaving group from the benzene ring. So you must have a leaving group on the benzene ring. We learned about activating groups and deactivating groups, which some of them are activating groups are ortho-para directors and deactivating groups are meta-directors. Halogens, they were kind of exceptions to the rule because they are deactivating at the same time they are ortho-para directors. The side chain reactions for oxidation of the side chain and halogenation of the side chain. We also learn about the Birch reaction when you only saturate one of the pi bonds and you end up with the cyclohexadiene. In chapter 18, we are starting with the new families, two groups or two family of the organic molecules. One is ketones and the other one aldehydes, or aldehydes and ketones. We again need to know how to name these compounds, what are some physical properties for these compounds, how to prepare these compounds, which we have learned some preparation method already, and we learned more preparation, and we reviewed the ones that we had learned before. Like if you oxidize primary alcohol using PCC, you get aldehyde. And if you use like a strong oxidizing agent, you would oxidize the primary alcohol all the way to carboxylic acid. But if you want to keep it aldehyde, you would use very mild oxidizing agent. You oxidize secondary alcohol, you get ketone. So at least we know some preparation method for the aldehyde and ketone. You have seen them before. From alkyne, you can hydrolyze alkyne and get enol. So you would get the tautomerization and you prepare aldehydes and ketones. So preparation, naming, physical property, then reactions. One chapter, chapter 18, covers all of these together. So we kind of have to go back and forth, have to name aldehydes and then learn about how to name ketones. But they are both family, they are known as carbonyl compounds. So aldehydes and ketones, what they have in common is the CO double bond. So you have that CO double bond that's in common, but ketone is attached to 2 carbon. That's CO double bond attached to 2 carbon. Aldehyde is attached to 1 carbon and 1 hydrogen. That's the difference. Other carbonyl compounds, which we learn in the future chapters, is the carboxylic acid, ester, acid chloride, and amide. But this chapter, we only talk about aldehydes and ketones, unless you want to do like a reduction of this to go to the aldehyde. So as just a preparation method, we can refer to that. So in order to study properties, we have to learn about the structure, the functional group. So we already know the functional group. We have a CO double bond, which is a polar bond. Carbon is positively charged slightly positive and oxygen slightly negative. It is a polar bond. So just like alkenes that we had, like a CC double bond, we had a pi bond. So alkene can go through addition reaction. Carbonyl group also can go through addition reaction because you just break the pi bond and you add two group, one to carbon and one to the oxygen. What can you say about the length of the carbonyl compared to CC double bond? What does it mean? If the carbonyl, the bond length for carbonyl is 1.23 and then for CC double bond is 1.34, what does that mean? There is another piece of information here that can help you with that. The bond energy or bond dissociation energy is much higher for CO double bond compared to the CC double bond. That means CO double bond is a stronger bond because the attraction between the opposite charges is stronger than this. Okay, so CO double bond is shorter, is stronger, and more polar than the CC double bond in the in alkene. How do you name ketones? What is the first step is to make sure that you have the longest carbon chain. That's the priority. If you learn about naming in alkane in chapter 3, then you should be able to name other groups with just addition of one new rule. So ketone has a functional group of CO double bond. And the last name or the suffix that is added is the ONE. So you basically drop an E at ONE. You have to number from the side that is closer to the carbonyl group, to the ketone functional group. So 1, 2, 3, 4. You have 4 carbon ketone, and the ketone functional group is on carbon number 2. That's why it's named as 2-butane. And then you drop the E at ONE, butanone. So 2-butanone, it comes from location of the CO double bond is on carbon number 2. And you have to number from left to right in this case because you want the carbonyl group takes the smallest possible number. You give the location and you separate number by dash line. There are total of 4 carbons, so it's a butane. And the functional group of ketone is designated by dropping the E and adding ONE, butanone. In second example, we have carbon 1, 2, 3, 4, 5. What would have happened if you go from left to right or right to left opposite? 1, 2, 3, 4, 5, no change. So it doesn't matter left to right or right to left. But the ketone is on carbon number 3. So you have to say at the end, you have to say 3-pentanone. When you say 3-pentanone, that means that you have named the main carbon chain, including the functional group. Anything that is not part of the main carbon chain, you have to name it as a branch. So you have a methyl group on carbon number 2, methyl group on carbon number 4. That's why it's got 2,4-dimethyl, and then 3-pentanone. Okay. So this is a ketone and is a mixture of the cyclic system and the open chain. The open chain has high priority functional group. So we have 2 functional group here. One is aromatic, the other one is ketone. Ketone takes the priority. And you would number the carbon chain starting from carbonyl group as carbon 1. And since the open chain is the major part of the molecule, you have to number this side. You have 3 carbon in the main carbon chain. And there is a phenyl group attached to this carbonyl group. You name that as the branch. So it's a 1-phenyl, 1-propanone. For cyclopentanone, you don't have to say one cyclopentanone because that takes the priority, and that would be carbon number 1 regardless of whatever. Okay, so when you say 3-methyl cyclopentanone, that means that the methyl group is in position 3 with respect to carbon 1 that carries a CO double bond. In this case, we have a cyclohexanone. At the same time, we have a carbon-carbon double bond. So which one takes priority, a ketone or alkene? Obviously, ketone takes the priority, and we had a list of the priority list, and we talked about it in the chapter 16. And you can look at the back cover of the book. It has the priority list also. The ketone takes higher priority compared to the alkene. So we know that is going to be carbon 1 assigned to the ketone. And we don't have to say 1 cyclohexanone because we already know. Okay, so the 2-in, okay, so when we have like a 2-in, you can include that into the name, and that would make it cyclohexenone. So when you say cyclohexenone, that includes the carbon-carbon double bond and then the CO double bond. You have multiple functional group here, OH and CO. First thing you do, you decide which one takes the priority. Oxygen, CO double bond is more oxidized than OH, or ketone takes high priority over the alcohol. And so we have to number from the side that is closer to ketone. And we have to name this as a branch because this is not a functional group. We cannot name this as alcohol anymore. We name it as a ketone. And we just say hydroxy for this OH group. Hydroxy group is on carbon number 4. There's a methyl group also on carbon number 4. So an alphabetic order, it would be 4-hydroxy, 4-methyl pentanone, or 2-pentanone, because we could have 2-pentanone or 3-pentanone. Any questions? Like in this example, even though OH is on carbon 1, but you still have to number from the side that is closer to the CO double bond. So if OH would actually be named or located on carbon number 4. So that gives like 4-hydroxy, 3-methyl, and 2-butanone. Any questions about naming ketones? Okay, no questions. How to name aldehydes? For the aldehydes, you drop the E and add Al, like more like alcohol. OL, in this case, is a Al. So it's always carbon 1 because it's beginning of the carbon chain, because one side has to be hydrogen, so it cannot be in between or in the middle. So it's always like carbon 1. So you have your, you don't have to say 1 to give the location. Is understood that is on carbon 1. You look for longest carbon chain. Whatever gives the longest carbon chain. So we have 5 carbon here. We are going from right to left because aldehyde is on carbon number 1. Carbon 3 takes the methyl group, so it would be 3-methyl pentane. So for 3-methyl pentane, and then you drop the E at Al. So alkane name, drop the E and add Al. That gives you 3-methyl pentanal. Okay. Ethanol or propanol, butanol, or like this is a pentanol. One thing you have to be careful with the condensed formula, when you have CHO, this means it's equal to C double bond H. when you have COH, this one is COH. So the difference between alcohol and aldehyde in condensed formula. So if you have a CHO, never make a mistake in that part with the alcohol. Is not alcohol. Is a HO, is not a OH. So if this is a aldehyde, and then we have a carbon-carbon double bond, which doesn't take the priority, but you have to give the location to that. So it would be 2-pentene al. So dropping the E, adding AL, it covers this part. And the in instead of ane is going to give you the carbon-carbon double bond. Just have to give the location. If you have a there is no cyclic aldehyde. Why there is no cyclic aldehyde? Because in a cyclic system, if you have C, part of the cyclic system is attached to 2 carbon. So it doesn't make sense to have cyclic aldehyde, but you could have aldehyde functional group attached to a cyclic system. Okay, so in this case, you would name the cyclic system and say carbaldehyde. And you say carbaldehyde, that includes the carbon and the aldehyde functional group. So cyclohexane carbaldehyde. The cyclopentane carbaldehyde. Cyclopentane carbaldehyde. 2 hydroxy group. The hydroxy groups on carbon number 2 of the cyclopentane carbaldehyde. Okay, if carbonyl group is part of high priority functional group, like aldehyde with ketone, carboxylic acid with aldehyde, carboxylic acid with ketone, then you can use the oxo. You would say oxo as a branch name for the carbonyl group. So just be careful when you say oxo, it doesn't include the carbon, it only includes the oxygen, double bond oxygen. So when you have one carbon, 1, 2, 3, 4, and 5. So between aldehydes and ketone, they are almost the same. They have same functional group, that you have carbonyl group in both of them. Why aldehyde takes the priority over the CO, or has high priority? Because aldehyde anyway is in the beginning of the carbon chain anyway. So they just made it easier. They said we are going to give the aldehyde high priority over the ketone. And later on, you will see carboxylic acid takes priority over ester because it's already beginning of the carbon chain. So aldehyde has high priority compared to ketone. So we are going to name this as a pentanal, and the ketone functional group with the location, it's oxo, 3-oxopentanal. In this case, you have carboxylic acid, and then you have like a aldehyde. If we had the only aldehyde here, it would have been benzaldehyde. But if you had only carboxylic acid, it would have been benzoic acid. Benzoic acid takes priority, so this is the parent name. We have to name this as a branch. Branch of COH, it looks like if you had another hydrogen, this would have been formaldehyde. Okay, formaldehyde. So if you have formaldehyde, you remove hydrogen, it's called formyl. Okay, so the formyl is basically the root name for, or a branch name for, formaldehyde. Is a formaldehyde has lost the hydrogen. So it's a formyl group attached to the benzoic acid. What location? Location 2. How do you determine location 1? Is the carbon that carries the main functional group, which is carboxylic acid. So this is 1, that would make sense. It's 2, obviously is not going to be 6. 3-oxobenzoic acid. Obviously, benzoic acid has the higher priority. You have 1, 2, 3, 4. So you have 4 carbon in the carbon chain, and that is going to give you a butanoic acid. And then you have a ketone functional group in carbon number 3 would be 3-oxo. Now, let me write a new example for you. Let's say if you have one side of the carbon chain is carboxylic acid. The other side of the carbon chain is aldehyde. What would you use for this branch? Obviously, numbering is going to be starting from carbon 1, 2, 3, 4. Now, if you name this as pentanoic acid, 5, okay, 5. So if I say this pentanoic acid, then I cannot say 4-mil group here, right? This is not 4-mil. Because if I say 4-mil, that means I'm doing CO double bond and the H. Okay. If I say CO double bond and H, if I name this as a 4-mil, that means I have to say butanoic acid, not pentanoic acid. I hope you get what I'm saying, what I'm trying to say, that if the aldehyde is part of the cyclic system, you name it as a 4-mil, but if it's part of the open chain, at the end of the chain, just use the oxo. Oxo means this part, okay? That's oxo. Should have used a different color for the oxo. So this part is oxo. This red part is 4-mil. So if you say pentanoic acid, which means the 5 carbon already counted, you cannot separate the 4-mil because then by mistake, you are giving extra carbon to your compound. So you just have to say oxo, and the oxo is in carbon number 5 in this case, and it's going to be 5-oxopentanoic acid. So 4-mil is used only in the cyclic, if it's attached to a cyclic system. But if it's attached to open chain, if it's at the end of the chain where you have your high priority functional group and the aldehyde is at the end of the open chain, you just use the oxygen as a branch and you say oxo as the branch. Questions? Any questions? No. Common name for ketone, they are known as the alkyl-alkyl ketone. So if you have the ketone, basically ketone CO double bond is attached to R group, which is alkyl group, and then another alkyl group. So you have the you name the alkyl group based on complexity or based on alphabetic order, and then you would just say that ketone. Okay, when you say ketone, is understood that you have CO double bond. So in this case, you have a methyl group and you have an isopropyl group. Then you say ketone. So methyl isopropyl ketone, alkyl ketone. That's like a general name for it. isopropyl in this case. And then this one is the alpha carbon. Carbon adjacent to carbonyl group is called alpha, and this is beta. So is alpha bromoethyl, alpha bromoethyl on one side, isopropyl on the other side, and ketone. Okay. If the two groups are identical, you can use you can combine it like a dimethyl ketone. In this case, you have a methyl ethyl ketone, but if you had a CH2CH3 here instead, you could have said diethyl ketone. So you can combine it. That's for the common name for ketones. Commercial name or historical name for some of the ketones. These were discovered or synthesized before even IUPAC rules. So we all know about acetone. Then acetophenone is a combination of a phenyl group. One phenyl group is replacing the methyl group in acetophenone, and then benzophenone, it's like two phenyl group ketone. Boiling point so that's about naming. Now, physical property, what do you expect? To have high boiling point or low boiling point compared to alkane? Compared to alkane with the same number of carbon, definitely aldehyde and ketone is going to have higher boiling point, because aldehyde and ketone, they have CO double bond, and that makes the molecule to be polar. And if it's polar, intermolecular forces is going to be dipole-dipole interaction. Dipole-dipole interaction is going to be much stronger than dispersion forces. As a result, you have almost same molar mass, but 49 degrees Celsius versus 0 degrees Celsius of the boiling point because of the dipole-dipole interaction. The stronger the dipole-dipole is, the higher the boiling point is going to be. So, when it comes to, if you're comparing to alcohol with the same number of carbon or same mass, basically, alcohol, they have higher boiling point because the intermolecular force for alcohol is hydrogen bonding, and hydrogen bonding is much stronger intermolecular force compared to dipole-dipole. Okay. Solubility in water for aldehydes and ketones. Solubility in water, it depends on the number of carbons that you have for aldehydes and you have for ketone. Because you have aldehyde and ketone, they both have a very polar CO double bond. So they could have like a dipole-dipole interaction, or they are hydrogen bond acceptors, and it can dissolve in water. But there is a cutoff. The cutoff is like 4 carbon. So if you have acetone in water, it would dissolve. Okay, acetone in water, it's going to, yes, dissolves. If you have a acetaldehyde, okay, or propanol in water is going to dissolve because you only have like 3 carbon. If you have 1 carbon, formaldehyde definitely dissolves in water because formalin is a 40% formaldehyde in water is used in like to preserve as a preservative agent, and it's used for tissues like animal tissue in like biology lab. When you see those containers, they're actually formalin, that they keep the tissues in there, human tissue or animal tissue in there, but sometimes they are using as a preservative for fruits and vegetables, which is a disaster they're not supposed to use it. And if they use it, like if you buy like a pack of strawberry outside, it looks very fresh. And then you cut the strawberries and inside is already rotten black. That means, you know, outside was covered by a reagent, like a preservative, strong preservative, or highly concentrated preservative, which is wrong, but it's done for money. And we just, there should be just more supervision. So aldehydes and ketones, they dissolve in water because they are highly polar. But like any other polar organic molecules, it depends on number of carbon. Even like alcohols, if you have 4 carbon alcohol, it dissolves. But if you have 6 carbon alcohol, it's not going to dissolve because even though you have the polar head here, it's polar, this side, but this tail is non-polar. If you have less than 5 carbon, the polar head is going to take the priority. But if it's more than 4 carbon, starting with the 5 carbon, the solubility drops, you know, significantly. And then like 6 carbon definitely doesn't dissolve. So the non-polar chain takes the priority. For aldehydes and ketones, carboxylic acid and alcohol, they're all the same. There's a cutoff of 5 carbon. 4 carbon and less, it dissolves. 5 carbon and more, it doesn't dissolve in water. But why even the 3 carbon or 4 carbon dissolves is because of the functional group that you have for the aldehydes and ketones, and it is acting as a hydrogen bond acceptor. So it dissolves in water. Questions? No questions? Can you hear me? Okay. You can or you cannot? Yes, okay. Okay, formaldehyde, preparation of the formaldehyde. They start from the, you know, oxane or trioxane. You heat it up, and then it changes to formaldehyde. Formaldehyde with water is the formalin that I was talking about, 40% formaldehyde in water. So if you put lots of water, you actually change the molecule to formalin because it's kind of an addition reaction. Water is being added to the CO double bond. When water is added to CO double bond, like any other hydration or addition of the water, it adds as a H and then OH. So you add H, add OH. H obviously you would add to the oxygen, right? And OH will add to the carbon. So you end up with a 2OH or diol, and it's known as the formalin preservative agent. Spectroscopy of aldehydes and ketones. You already know these spectroscopies, and it's the CO double bond, major functional group for both of them. It shows bond at 1710 for ketone, 17, you know, between 1710 to 1725 for aldehyde. But for aldehyde, you must have a set of 2700, 2800 peak also. For aldehyde, for ketone, it's just a 1700 or 1710 and it's not. If it's a cyclic ketone, the CO double bond in the cyclic system is going to have a higher number. For cyclopropanone, it's even much higher than the cyclopentanone. Conjugation lowers the frequency because this carbonyl group is conjugated with a CC double bond. it drops to 1690. If it's highly conjugated with the benzene ring, it's conjugated with 3 other pi bonds, it's even lower, and that is a 1685. So if it's lower, if it's conjugated, it's going to be lower. The frequency is going to be reduced. Okay. Okay. NMR for aldehydes, proton NMR would show a peak between 9 and 10. That's for proton NMR, and that was exam question. And since we refer that to like multiple times, a peak between 9 and 10, it would designate aldehyde. I was really surprised when I saw like, that a couple of students, they missed it. But 9 and 10, it would be the hydrogen of the aldehyde. Alpha hydrogen, we're going to learn about alpha hydrogen as a whole chapter if you have time for the semester, is the carbon adjacent to CO double bond, is known as the alpha hydrogen. Alpha hydrogen or alpha carbon, or as a result of that would be alpha hydrogen. Hydrogen attached to alpha carbon is known as alpha hydrogen, is going to shift to higher number by like 1 unit at least. So it shows a number at 2 over 2. So if you have a CH2 that is at 1.4, then you add like a 1.1 to that, is going to be like 2.5. So you see this alpha is showing peak between 2 and 3. The further away, beta and gamma, if the hydrogens are further away from the carbonyl group, the electron withdrawing effect is going to be less significant. And because it's less significant, it's going to be shifted. It's not like this CH3 is not going to show at 0.9, it would show at 1. Still, it would be affected, but not very significant. But what is very significant is the bond between, a peak between 9 and 10 for aldehyde, and then the alpha hydrogen that is, shifted by 1 or 1.1 unit to higher numbers. The carbon-13 NMR, it would show a carbonyl group at like a third quarter or higher than 150, or between 160 to 200. So you see that for carbon-13 NMR is going to also show, just like aldehyde, that it was at the end of the scale for proton NMR, aldehyde for carbon-13 NMR also is going to be at the upper level. The cleavage at alpha carbon or carbonyl group with adjacent carbon is very popular in mass spec. So often you see the fragments that is generated by cleavage on both sides of the carbonyl group. So you could have like you could have a mass that represents the left side, or a fragment that represents the right side of the alkyl plus the CO double bond. So this is kind of, it's more in-depth of studying of mass spec. Obviously for organic chemistry, we didn't spend that much time because it's part of just another chapter of IR, and we don't get that much of time to study mass spec in depth. But is one of the pattern, like a cleavage pattern or fragmentation pattern for ketones. It could be on both sides. The cleavage can happen on both sides. This cleavage is very popular, and you could see a mass that includes the CO double bond and one of the alkyl groups at the time. For the UV light or UV spectroscopy, CO double bond has a peak on its own, and then if it's conjugated, it's going to add up by like a 30 unit. So it's very, it's helpful to find if it's conjugated or is not conjugated. So you have to have the base and then add the conjugation. Some uses of the aldehydes and ketones in industry, acetone and methyl ethyl ketone, these are good solvents. Formaldehyde is used in polymers, and also flavoring. They're used in the in flavoring also, like the cinnamaldehyde, that is a we find in the cinnamon and other food. Acetophenone, if they don't want to add pistachio to ice cream, they can use acetophenone and it tastes like pistachio. Vanillin has an aldehyde functional group, so vanilla has the vanillin and is used in the in food and perfumes, and so these are some of the applications or industrial usage of the aldehydes and ketones. Okay, questions that you might have.